Welcome to the Unit 8, Section 3 video on graphing and interpreting quadratics. The standard form of a quadratic function can be described as an equation of the form y equals ax squared plus bx plus c. We've worked with this form already quite a bit. Now, the direction of the graph is going to be determined by your a value, your leading coefficient. If your leading coefficient is positive, then the graph will be concave up. If it is negative, then the graph will be concave down. The y-intercept is where the graph crosses the y-axis. It is your value of c. So whatever your value for c is, that is the y value of your y-intercept. The max occurs when the parabola is concave down. The min occurs when the parabola is concave up, and you can get that information from your a value. The axis of symmetry, when you're in standard form, uses the formula x equals negative b over 2a. The axis of symmetry is the vertical line that splits the graph in half. And that axis of symmetry does give you half of your vertex. It gives you the x value of your vertex. You can plug the x value of the axis of symmetry into the equation to find your y value. The vertex is either the highest or lowest point in the graph. It's either your max or your min, depending on the orientation of your parabola. So let's identify each key feature. So for this function, the direction of the opening is concave up because a is positive, a is 2. The axis of symmetry is going to be done using negative b over 2a. In this case, b is 6, a is 2, so we're going to plug those two things in. Get negative 6 over 4, which is negative 3 halves. The vertex can be found by taking the axis of symmetry, the x value for your axis of symmetry, and plugging it in for your x value in your equation. And after a little bit of solving and simplifying, including finding some common denominators, we get y is equal to negative 11 halves. Now remember, this is asking for the vertex, so it needs to be an ordered pair using both your x and y values. And then finally, the y-intercept here is at 0, negative 1, because your c value is negative 1. Your max and min value, you have a min at y equals negative 11 halves, and you can pull that from the y value of your vertex. And it is a minimum because the direction of the opening is concave up. For this example, let's get the direction of the opening. That would be concave down because it is negative in that leading coefficient. The axis of symmetry, take your b and your a values, plug them in, and simplify down to negative 1. Then use that negative 1 in your function to find the y that goes with it, which would be 11 halves. So now we have negative 1, 11 halves is our vertex. The y-intercept is 0, 5, because 5 is your c value. And we have a maximum, since we are concave down, and it is at the y value of 11 halves. To graph in standard form, you're going to find and graph the axis of symmetry, determine and plot the vertex, choose 2 points on one side of the axis of symmetry and plot them, reflect these points across the axis of symmetry, and connect with a smooth curve. So, let's find the properties for this one. The axis of symmetry is negative b over 2a, so we plug in b and a and get 2. The vertex, plug in our 2 from the axis of symmetry for x to get the corresponding y value, so that gives us our vertex. Now let's find a couple of additional points. So since our vertex is along x equals 2, I'm going to use some simple values going to the left of that vertex, starting with x equals 1, and then going to x equals negative 1. I skipped 0 because 0 is easy to get because it's just your y-intercept, which would be 2. And here it is graphed for you. You can see that we graphed the axis of symmetry using the dashed line. We have our vertex. I plotted the first point, which was 1, negative 1. We plot the y-intercept, we plot the second point, and then you reflect those points across the axis of symmetry, and then connect it with a smooth curve. For this problem, our axis of symmetry can be found, again, using x equals negative b over 2a, and in this case we get 2. Plug in 2 to the original equation to find the y that goes with it, and we get 2, negative 4 for our vertex. And since we use 2 and we have a 1/2 in the front, I'm going to use even numbers here to make sure that we end up with some whole numbers. So I'll start with 0. That is our y-intercept, and you can pull that straight off the equation because that is our c value. And then for point 2, I use negative 2, and I get negative 2, 12. And there is the graph once you have it completed. In the vertex form of a quadratic function, it can be described as an equation of the form y equals a times x minus h quantity squared plus k. Again, a cannot be 0 because if a is 0, terms go away and it's no longer a quadratic function. The direction of the graph doesn't change. If a is positive, the graph is still going to be concave up. If a is negative, the graph will still be concave down. The y-intercept will be found by substituting 0 in for the x value and simplifying. Our maximum minimum point still depends on the concavity, which again stems off the sign of your a value. The axis of symmetry is still going to be your vertical line that splits the graph in half. And in this case, we are going to use the value for h. So the axis of symmetry is fairly easy to find in vertex form. And for the vertex, that's easy to find as well, because it is the ordered pair hk. H is your x value, k is your y value. So let's identify each key feature in vertex form. So for this one, the direction of the opening is concave down because we're leading with a negative. The axis of symmetry is your h and k. So h is 2, k is 3. So we have 2, 3 for your vertex. Axis of symmetry was the x value, which is 2. That's your value of h. The y-intercept we get by substituting 0 in for x and solving, and we get negative 1. So the y-intercept's at 0, negative 1. And we have a max at y equals 3. 3 comes from your vertex, the y value of your vertex, and we have a maximum because we're concave down. In this function, we have concave up because the leading coefficient is positive. The axis of symmetry is your h value, so here it's x plus 1, which is the same as x minus negative 1. So h is negative 1, so your axis of symmetry is x equals negative 1. The vertex is negative 1, negative 6. That's just your h and k value. The y-intercept you get by plugging in 0 for x and solving to get the y value, so it's 0, negative 2. And since we're concave up, we have a minimum at y equals negative 6. Again, that negative 6 coming from the y value of your vertex. So to graph in vertex form, find and graph the axis of symmetry, determine and plot the vertex, choose 2 points on one side of the axis of symmetry and plot them, reflect these points across the axis of symmetry, and then connect with a smooth curve. So we are going to graph the following quadratics by finding their properties. Starting with this. Here we have an axis of symmetry of x equals 2. That is our h value. Our vertex is hk, which in this case would be 2, 1. We're going to find 1 point on the left of your vertex, which would be 1 for your x value. Plug that in to solve for y, so we get 1, 3. And then let's back it up to 0. If we plug 0 in, we get 9 as our y value, and we get the point 0, 9. Graph these points, graph your axis of symmetry, and then reflect your points across your axis of symmetry and connect with a smooth curve. For this function, our axis of symmetry is at x equals negative 1. That is our h value. hk gives us our vertex, negative 1, negative 3. Since our vertex x value is negative 1, let's go to the right and go with 0 to get negative 6. So 0, negative 6 is a point. Let's move on to x equals 1 and put 1 in, and we get 1, negative 15. And then we can graph the points, graph our axis of symmetry, reflect the points, and connect with our smooth curve. When interpreting word problems, it is helpful to understand how to interpret what is being asked for in relation to the corresponding quadratic key feature. So when the wording says something like maximum height, you're going to be thinking about the top of your parabola, so you'll be thinking of the y value of the vertex. When you hear how long does it take to reach the maximum height, your time is going to be along your x-axis, so that would be the x value of your vertex. The starting height would be the very beginning of your parabola at x equals 0, so that would be your y-intercept. And the time it took to reach the ground would be the other end of your parabola, that would be your x-intercept. Selecting the appropriate key feature provides a procedure for determining the solution for a real-world problem. So let's take a look at this example. The height in feet of a football that is kicked can be modeled by the function f of x equals negative 16x squared plus 64x, where x is the time in seconds after it is kicked. So we're given the equation to use. We just need to figure out what we want to pull from this equation for what is being asked. So the first thing we're being asked is, what was the starting height of the football? So starting height, we're going to be thinking of the y-intercept. So we want to find the y-intercept by plugging in 0 for x. And when you do that, you end up with 0 feet. So the starting height of the football was 0 feet, which makes sense. You would imagine that when you're kicking off a football, it starts at the ground. How long did it take for the football to reach its maximum height? So now here we're looking at the vertex because we're looking at the top of the parabola. And for time, we're going to be looking at the x value. So we want the axis of symmetry, x equals negative b over 2a, because we know that the axis of symmetry gives us the x value of our vertex. So we're going to take b and a and plug them in, and we'll evaluate to 64 over 32, which gives us 2 seconds. And remember, on all of these problems, you need to make sure you include the units as part of your answer. What is the maximum height of the football? Well, now we want the y value of our vertex. We just found the x value, so we can take that x value and plug it in to our quadratic equation to get the y value that goes with it. And the y value we get is 64 feet. As Molly dives into her pool, her height in feet above the water can be modeled by the function f of x equals negative 16x squared plus 16x plus 12, where x is the time in seconds after she begins diving. How high is the diving board? This is going to be her starting height, so we're looking for our y-intercept. So we're going to plug 0 in for x, and we're going to get that our starting height is 12 feet. How long did it take for Molly to reach her maximum height? So again, since we're looking for the time that she's at her maximum height, we're looking for the x value of our vertex, which can be found using the axis of symmetry, x equals negative b over 2a. Plug in your b, plug in your a, and simplify to get 1/2 or 0.5 seconds. And think about it, it does make sense that she'll reach her maximum height about 1/2 second into her dive, because she'll jump up off of the diving board and almost immediately gravity is going to pull her down. So she's not going to be going up for very long. Most of her flight path is going to be going down. What is the maximum height of Molly's dive? Well, here we want the y value of our vertex. So we're going to take our x value, plug it in, use our calculator to find that we have 16 feet as her maximum height. So she sprung off the diving board from 12 feet up to 16 feet, so she got about 4 feet into the air before she started coming back down. Thanks for checking out my video in the Foundations in Algebra series. You can subscribe to my channel. I've got the next video queued up for you, and if you need to check out any of the videos in the course, I've got the course playlist for you here as well. Thanks for watching.